My name is Nuno Rosso, and I'm the technical coordinator of the Better project. And I'm here doing a general presentation, a general overview of the Better project, representing a wide team coming from different partners. Some of the names are there in this first slide. So our aim is to deliver EO-based data pipelines to address key societal challenges. This concept of data pipelines and data challenges will be defined in more depth in the following slide.
Sorry, Nuno, we lost you again. You're muted again.
Sorry, I didn't understand how that happened. But so just to move on, the Better is like the other projects in this hackathon, 3-year 2020 project selected in the EO2 2017 called Big Data Shift. It has 6 partners. Some of them are connected with the technical development of the service layer of Better, and others that are challenge promoters, that are users that are driving the requirements, that are setting out the requirements and driving the development of the platform. So the technical development part is handled by the three companies within the Demos group. So Demos Engenharia based in Portugal, Demos Space based in Spain, and Demos UK. Terradue, which is handling the Elite framework platform, and the Fraunhofer Institute for Intelligence Analysis, which is coming with their knowledge on semantic analytics, and I think there will be a presentation on that for one of the exercises of the hackathon. And within the Demos group, Demos UK, that has the machine learning expertise for classification in satellite imagery, or for feature detection in satellite imagery, and there will be an exercise dedicated to that also, and Alireza will do the presentation on that. And then the challenge promoters are composed of the World Food Programme, working on the food security part, on the geospatial intelligence, the European Union Satellite Center, SATSAN, and on geohazards, the Swiss Federal Institute of Technology in Zurich, ATH Zurich. So those are the ones providing the challenges that the platform and the service layer of Better would need to reply to. So I hope that this concepts of data challenge and data pipelines become a bit clearer with my presentation. So the general objective of Better is to implement the EO Big Data intermediate service layer. So it's not a focus on only on technologies and tools. It's also about the process of establishing a EO processing chain that's able to handle big data. And that service layer is devoted to harnessing the potential of Copernicus and Sentinel European EO data directly from the needs of users, which are gathered through those data challenges, as I said. So that's why we have the challenge promoters within the project, and delivering to them customized solutions that denominated data pipelines. And the data pipelines are those processing chains and those different components of the platform that allow the challenge promoters to receive the systematic flow of data following the requirements set by the data challenges. So in terms of the different layers that are being set out by ESA and by the European Commission, we see ourselves in between what is of the platform service layer and exploitation layer. So we cover both of those upper layers of this ecosystem that you see represented here in the slide. So the data challenges are set by user communities, represented not only by our internal challenge promoters, but also by external challenge promoters that I will present later on, to drive the development of the Better service layers. We have organized ourselves in yearly cycles of 3 challenge yearly cycles, where each challenge promoter provides, if they're an internal challenge promoter, 3 challenges. If they're an external, only 1 challenge per challenge promoter. They are working in key societal areas, and the challenges that they present should consist of a well-defined problem that requires systematic processing of EO and or non-EO data. It should involve high data volume and or diversity. That's why we're talking about big data. And it should be centered in the use of Copernicus and Sentinel data. And why this approach? Our approach is indeed to improve what is the Better service layer, and our approach to that was to have a wide variety of challenge promoters being able to deliver challenges for the project. And by doing that, we address the needs of a diverse set of user communities and promote a wider range of solutions. And that increases the scope, robustness, and resilience of the better service layer. And you can see here at the top of this slide, the 3 internal challenge promoters, but we have already on board several others that are either already we are implementing challenges for them or are in the pipeline to be challenge promoters within better. So we are currently in the end of the second challenge cycle. And not only we have challenge promoters from these 3 entities, but also from Aarhus University, the World Customs Organization, Fidelidade Seguros, which is an insurance company here in Portugal, and the National Institute of Geophysics and Volcanology in Italy. So what do the challenges provide to better? In very broad terms, they improve the data pipeline development process from the user requirement definition to personalization. There's a learning process that we are going through with the 2 different challenge promoters to make this process more agile and more efficient. It increases the EO and non-EO data portfolio, so their data requests increase our data portfolio as a service. It optimizes pipeline triggering, processing, and delivery methods. That's where most of our, let's say, technological or tool-based improvements are based on. It's in this optimization of pipeline triggering, processing, delivery methods, and then you're able to improve the information content of the different pipeline outputs through semantic data representation in machine learning analytics. And this is represented here by SANSA and the artificial intelligence classification application that the Musique will present. SANSA will be presented by Fraunhofer. And those 2 components are more on the application side. So each time there's a pipeline delivering systematically a specific pipeline data stream, someone on the end of that pipeline data stream can then perform some on-demand application over it. And that's the main focus of the exercises for this hackathon. So just to do a small summary of the first challenge cycle, we're already in the end of the second, but just as an overview, we had 9 data challenges in total involving 17 different EO input data streams, delivering to promoters 41 different output data streams, 6 global or near global, and other outputs include 15 different AOEs around the world. I will not go through the different data challenges, but I wanted to highlight the 2 that are going to be the basis for the exercises presented by both the Musique and the Fraunhofer Institute. So for exercise 1 and 2, so exercise 1 is going to be led by Terra Due. They cannot attend this webinar, but the exercise is rather simple, so you'll be able to follow it within the hackathon. But this data pipeline will be the input both for exercise 1 and exercise 2. Exercise 2 will be presented by the Musique, as I said, for land cover changes and interannual vegetation performance analysis using machine learning algorithms. So this pipeline is basically delivering regularly, and each time there's a new Sentinel image this is processed, it's able to generate a time series of analysis-rated data of vegetation indexes from Sentinel-2 products, including atmospheric correction, with a suitable algorithm. In this case, I think we're using Sent2 Core, but I'm not completely sure. And then so it's not only delivering these vegetation indexes, but it's also delivering bottom of the atmosphere reflectances. This is a bit of summary of the resources available and where it is deployed currently in terms of the cloud infrastructure. The better service layer is cloud agnostic, so we can deploy it in different cloud providers. And these are the promoters behind the challenge, in this case, WFP. So for exercise 3, the pipeline outputs that are going to be used by Fraunhofer are being generated also for another pipeline developed for WFP, and that's providing aggregations, so aggregated temporal moving windows aggregations from CHIRPS precipitation daily data, 5 kilometer resolution. So it's basically sums over the past n days, counts of daily data that has precipitation above 1 millimeter, or longest sequence of daily values lower than 2 millimeters, what's called a dry spell. So all this aggregations were compiled within the framework of a challenge where WFP wanted us to calculate anomalies over these data sets. And so this will be the input for service 3. And I'll finish here the presentation for the overview of Better. Thank you very much.
Thanks, Nuno. I think with that, then we go to one of our first two dives into what to expect at the hackathon from the Better point of view. So we will next go to Ali Reza from the University UK. In the meantime, for those joining live today, if you have any questions, you can ask them using the GoToWebinar app, and we will have a round of them later. So Ali Reza, please go ahead.
Okay, thank you, Simon. And thank you very much, Nuno, for your comprehensive introduction to Better Project. I would like to introduce myself first. I'm Ali Reza Tarabat, and I'm a senior remote sensing data scientist in Demospace UK. Before starting this presentation, I would like to thank two of my colleagues who helped me a lot preparing these slides, Patrick and Matt. As Simon mentioned, the overall objectives of this webinar is to give you an overall idea about the activities we are going to do in Horizon 2020 Earth Observation and Big Data Hackathon next month in Frascati. But the detailed objective of my presentation is to first give you some overall idea how to prepare for the hackathon for the second exercise, which is linked to Better AI, which stands for Better Artificial Intelligence Framework. Then I'll give you some idea about the exercise sections we are going to do during our hackathon day. Then I'll give you some technical introduction to the framework we're developing here in Demospace UK in the context of Better project that we call Better AI framework. And at the end of my presentation, I'll provide you a list of several references you can refer to if you want to get more information about the algorithms which we developed and which we use in Better AI framework. In the second exercise, we need to have a laptops with a high GPU capability. So if you want to really get good results out of that exercise, you should have a laptop with a good GPU capability. But at present, we are in touch with European Space Agency in Frascati and communicating with them to see if we can use ESA's laptops for those who don't have a proper system for this exercise. If we can succeed to get permission to use laptops from European Space Agency, we're going to install the required packages and softwares for exercise number 2. Otherwise, we will provide you a tutorial to install Better AI application. And then we also recommend you to have QGIS on your laptop, because at the end of the exercise, we will visualize the data in QGIS. If we do some visual interpretation to see the results of different algorithms generated from Better AI framework. I should mention that all the exercises we will conduct will be based on Jupyter Notebook. So if you have some experience with Jupyter Notebook, it would be great. Otherwise, I suggest you to read a little bit about Jupyter Notebooks, the basics of use of Jupyter Notebook to see how it works, how to run single blocks, and so on. And as far we have a limited time for the second exercise on the hackathon day, I suggest you to prepare your questions prior to the hackathon day and send me by email that question so I can answer them. Then, yeah, because most probably we won't have enough time to answer all the questions during that exercise. The training database we will provide you is from Denmark. It's an area of interest in Denmark. That's an example of one of the area of interest we're going to provide you. And we'll apply cloud classification and field boundary detection in this study area. First, we will apply field boundary detection we will get the results out of field boundary detection algorithm, and then have used the outputs of field boundary detection as input of crop classification model. The exercise sections are as follows. We first work on a data pipeline discovery using OpenSearch API in the Jupyter Notebook. So using the Jupyter Notebook, we will provide you will access a TODOS platform to retrieve some data for our study area. And then out of the data we're retrieving, we will select the best day to focus on based on the cloud cover, if there is any sun glint on that study area for that specific date or not. And then we download the Sentinel-2 level 2 images for the next and further steps, for the classification segmentation steps, of course. As I mentioned, we are using better AI classification application. So we use the same framework to pre-process training data and prepare them for machine learning classification. And then if we've got enough time, we're going also to train different classification algorithm using the open training data sets that we will provide you again during the training session to use. And then we also assess the training and validation outputs and evaluate the results of different algorithms we will train, and so on. If we don't have enough time, we'll directly perform classification using pre-trained models we are going to offer you. There would be two models. First model is image segmentation model for field boundary detection, and the second one is the algorithm which is pre-trained for crop classification over Denmark. And then at the end of the session, we will visualize the results in QGIS. We compare the results.
Alireza, I cannot hear you anymore. Or is it just myself?
Hello.
Hi. Yes, now you're back.
Hello. Can you hear me now?
Yes.
Can you hear me now?
Yes, indeed.
Hello.
Yes, please proceed, Alireza.
Okay. Okay, you can hear me. I'm sorry. Okay. And then we have a scripting module in our platform, which is being used for automatizing the procedures for training and classification of the different convolutional neural networks model. We have a vectorization module, labeling component, data collector component, and a set of codes for training, classification, and evaluation. And we have a module called classification components, which has a very specific Python code in it for training data factory, which gives us the capability to train, to pre-process the data for injecting to different models for training different algorithm. And then we have a CNN classifier module, which is the core module in Beta AI with different convolutional neural networks algorithms in it, which you can just go through it and select different algorithms, which can be used also for training and classification. A few of these algorithms are pre-trained algorithms, so you can directly use them without any training. The whole Beta AI is being developed at present in DemoSpace UK and is being used actively as a deep learning platform. We use it in our we use this Beta AI as our daily classification and segmentation framework. And I should also mention that all the deep learning modules we have used in Beta AI are based on TensorFlow and Keras. So if you have experience of using TensorFlow and Keras, you most probably won't have any problem of using Beta AI, because most of the functionalities are based on TensorFlow and Keras, of course. For training models in Beta AI, we created a very specific script which you can use for automatizing the training steps. But before starting the training, it's very important to split your training data into training and validation data set. If you don't do that, Beta AI automatically generates training and validation data set out of the data you're giving to the framework. So if you're searching for a very specific standard or procedure for training and classifying your data, it's better first to separate your data into training and validation to be 100% sure that you're in a proper path of your methodology. There are several variables which can be used and changed to optimize and tweak the model learning methods. And you can optimize them, you can tweak them, even you can put those parameters in a for loop. So you can try different types of combination and train train one specific model by different type of parameters adjustment to see what are the effects of those parameters into training phase. For monitoring the model training, we use Tensorboard. So if you're familiar with TensorFlow, you most probably know Tensorboard as well. And we are using the same platform for checking and observing the training performance in different models. And at the end of the training, you can simply execute classification.py script, which gives you the flexibility of using different algorithms for your final classification based on different parameters or based on your pre-trained model. Here, I'm going to give you an example of a bad training based on TensorFlow. As you can see, we have validation loss function, which is increasing a little bit, which shows the overfitting in your training phase. So it means that the model you're training is overfitting, while the loss function in the top right, it somehow is, it's just going as a line in different epochs. So it shows that the model is overfitting. We have a very nice feature for FMeasure for validation of a single class, which also gives us some idea if the model is not learning for a single class. If you see in the middle top graph, the validation of measure is increasing. So it shows that the model has some problem in training. But again, the validation of the single class in FMeasure also is decreasing, which shows that the model is not training well for a single class. This is a good training example we have based on TensorFlow. As you can see, the loss function top right goes down smoothly. So it shows that the model is training very well smoothly. You have a validation loss function on right down figure, shows that also the loss function is really decreasing nicely. And in general, this combination shows that the model is training good. So you should expect somehow a good result out of this model. But which type of results you should expect, for example, for field boundary detection based on the model we are going to train, or the results we are getting out of the pre-trained model, should be similar to this one, which is a probability map. And in this one, the red color are the segments which we are not interested in. The blue colors are field boundaries, and the green colors are croplands. I should mention that we're not dealing with edge detection algorithm. We're dealing with a field boundary detection. What does it mean? It means that if you have forest, urban, or water body in your image, the field boundary detection algorithm doesn't detect the boundaries of those features. It just detects the boundaries of the fields. So it's not edge detection algorithm, it's a field boundary detection. After pre-processing steps, you should get something like this, which shows the exact field boundaries in our study area. The results you should expect from fruit classification algorithm should look something like this. Each color shows the different crop types in our study area. We can visualize these results in QGIS and see and calculate the final accuracy of the classification. However, we will get also a proper accuracy matrix of the algorithm performance and also the accuracy of the final outputs like confusion matrix. Here is the list of several peer-reviewed publications which are published in remote sensing journals, and these publications are about using convolutional neural networks, or let's say machine learning algorithms for cropland monitoring, like crop type classification, field boundary detection, and so on. If you have any questions regarding these papers also, I would be happy to answer them if you send to me by email. Thank you very much for your attention.
Thank you, Alireza. So if there are any questions from the people who joined today, reminder that you can ask them and we'll answer them. So we will go next to actually our edition. So there's Mohammed who will present, but in short, I wanted to introduce a bit. So basically, this is part of the hackathon for the better session. Will be a bit more innovative, let's say, experiments in the project. And so more research applications, but also quite cutting edge. So the point is semantic analytics, and here is the idea that once you can obtain data, could be in different formats, if it can be uniformly transformed into RDF in this case, then there are tools which we are leading, semantic analytics, so high scalability over RDF data, which can process the data and perform analytics on this form of data. And this is very interesting, especially since today, Better and the Open are having this joint webinar in preparation of the hackathon to, for example, identify potential collaborations within these projects. So this is something which we will use the hackathon Frascati, use the opportunity of the hackathon Frascati to identify. Both projects have semantics, so they will or are already dealing with RDF data. And the nice thing about this is that if there are different data sets being considered by both projects, once they are successfully transformed to RDF data, it makes it much easier to, for example, bring together the data from eOpen and vice versa, of course. But now we'll show you what we intend on showcasing in Better. So we can bring in the data from eOpen and combine it with our data in Better to perform joint processing on this, let's say, integrated, rather than integrated, more like uniformly transformed data, so that can be ingested by our semantic analytics tool. So I think that gives a bit of a good overview of this, the value in this. And I would just give the floor to Mohammed to introduce this.
Yeah, good morning, good afternoon, everyone. Hello, everyone. Yeah, the semantic analytics that we are offering as part of the Better project are provided by a software that we have been building for some time now, and it is maturing and it's open source, and it's going on its way to the 6th release, public release, and it's been worked on by members from three institutions: University of Bonn, University of Leipzig, and Fraunhofer Institute here. So it is a platform for processing, analyzing large-scale knowledge graphs, or RDF. And it is unique in its capabilities. I will explain all the 5 layers here, but there's no similar platform with that comprehensive coverage of processing. So the very bottom layer is a distributed in-memory processing. It's there where the processing is effectively executed. And for this, we use existing state-of-the-art in-memory big data processing engines. For example, if you know Apache Spark and Flink, and this allows us to scale to large knowledge graphs and perform efficiently processing over them. Then the higher layer is the knowledge distribution and representation. Basically, this is the layer that is responsible for loading the data and shaping it and representing it in a formal internal representation, and that is optimized for this type of data and processing. And then we have the third layer from the bottom is the querying, which is the layer that is responsible for querying this data that has been loaded and represented in this optimal format. And we do this querying using a one-query language, which is called Sparkle. And then the next layer is called the inference layer. This functionality, this inference as a general concept is specific. It's specific to the knowledge graph and RDF model, and we don't find it in other data models. So it's one of the great points about using knowledge graphs and RDF. And its principle is basically allows us to expand the data and generate new data that based on the data that we have. So we use some rules that allows us to make explicit some implicit data. So basically it's a data that we have but implicit, but using a set of rules, this allows us to generate a new data. And of course, new data means new value. And then the last layer, which is what we are the most interested with, is the machine learning. And we luckily managed to implement a lot of state-of-the-art machine learning algorithms on top of knowledge graphs in this specific format, RDF. So you will probably recognize embeddings. You will recognize, for example, clustering, association rule mining, decision trees, and all those over knowledge graph, our canonical format that we support and work with. So we will give a bit of more details in the 2 lower layers, which is the data representation and processing. So basically, we accept the knowledge graph in RDF format, which is stored in Hadoop. Supposedly, it's really large RDF data that is stored in a cluster, in a Hadoop cluster. And then we partition this data. We represent it internally in a form that is optimal for our processing. For those who know, it's called the vertical partitioning. And then once we have the data in this optimal format, we load it into in-memory, which you can see the second step generates distributed data structures that are stored in memory, and they're optimized for distributed and large-scale processing. And then the user run the query over this data, and internally this query is translated into relational views, because this distributed data has a tabular format. So relational views are created, just virtual views, and it allows us to actually extract the data. In order to showcase some of SANSA merits or capabilities, we will showcase an application or use case, both here, and it will be also presented in the hackathon, more or less. Basically, we will make use of CHIRPS rainfall aggregates data and crop market prices and crop production, and we try to detect patterns and correlations between these data. Basically, the process goes through 3 main steps. One is we ingest this CHIRPS data, but into a knowledge graph, in a knowledge graph representation, and we base this on existing specific ontology. So basically, you can see ontology as a model or a schema that allows us to bring data from one format, which is CHIRPS data, which is GeoTIF data, into this triple RDF data. And we next interlink this data with some existing open data that we can obtain freely and openly. For example, looking at the crop market prices from WFP or crop production from FAO. And we link this and we try to come up with interesting use cases. And then the last is one example of such a use case would be to detect patterns and correlations between the values of these three data sources. So we divide this process into 3 workflows, which we envision that this will be more or less what we will present in the hackathon. So basically, the first workflow will take us from images to at the end to knowledge graph RDF data. So basically, what we have at hand is CHIRPS data about the whole Southern African region, and we are interested in knowing or correlating these values, these rainfall values, with corn prices and production on a specific country on a specific period. So we first start by taking the rainfall values from images. We extract them using Python pipelines, and then we convert these values into or not convert, but extract what these values correspond in the map in terms of geographical coordinates. And then the next step would be to obtain the border polygon in terms also of coordinates of country of interest in the Southern African region. And then we do an intersection, geographical intersection between the whole region and only the country of interest in order for us to be able to get only the rainfall values of that specific country. And the last step would be the transformation. We transform this data, which is in tabular format, into the knowledge graph RDF format, which is triple format. And again, here we base on existing ontologies or models that allows us to generate RDF starting from these rainfall values. So this is more or less the visual representation of this workflow. So we start with CHIRPS rainfall values from a GeoTIFF file of a specific month, and then we go through all these pipelines. So first we extract the values, which are the rainfall values, and then we extract the geo coordinates of the whole region, and then we take the coordinates of the country of interest, and then we intersect these two, and so we have only the rainfall values of that country of interest, and then we do the transformation, or what we call here RDFization of the data, and then we have as output RDF data. The next workflow, this one, is to obtain data from some open data portal that's potentially interlinkable with the data that we got from GeoTIFF rainfall data. So we have as an example the market price of corns that you can obtain from the WFP, the open data portal, which is in a CSV format. And then we filter this data to obtain only the month or the months that we are interested in. And then again, we also do the transformation to generate data in the RDF knowledge graph model. And then we reach to the point where we do apply machine learning, and the algorithm that we will be experimenting with is correlation detection. So for this work, we the user provides data about or the files that they want to extract from correlation, basically. So they provide data that come from the very first pipeline, which is the rainfall, and also data about price markets, for example, in RDF. And using some configuration of files, the user can tell which property in this data or which properties we want to detect the correlation between them. And then we using Scala, we create vectors out of these properties, and then we pour these vectors into a correlation detection algorithm. And the one that we are using at the moment is Pearson method. And this is using Spark because we want to apply this in a large scale environment, and Spark is an engine that allows us to do that, and it has this correlation detection algorithm using the Pearson method. So as you can see, also a visual representation starting from data to vectors and then correlation detection. And more practically, what we are going to demonstrate is we take the rainfall values of a month X, for example, and then we extract the 3, 4, or 5 months prices of the corn of interest of any corn, and then we slide the month of interest to the second month Y, and then we also slide the 3, 4 months to the next 3, 4 months. For example, we take the rainfall of January and take the prices from February, March, April, and then we take the rainfall of February, we take the prices of March, April, May. And this way we can notice if there's any pattern, any correlation between the rainfall and the prices in the next couple of months. And we can do the same with corn production or yield. It would be exactly the same process. It just differs on what data you give as input. So yeah, that would be more or less what we have in mind at the moment, and all the participants will be provided with the material, which could be publicly downloadable, and we can help them configure their machines. So keep in mind that you will be use Python, Spark, and possibly Scala if you want to touch some code. But again, everything will be provided, and we will be ready to support.